All right, so second part of topic 2.2, motion or charged particles in electrical field. It's got to do with if you now introduce other velocity vectors into your parallel plate, into your uniform electrical field, what's going to happen? And it's actually surprisingly simple because it follows a projectile motion as normal motion. So we established that parallel plates introduce a uniform field. So, and the field is denoted by E, which is electrical field strength, which is kind of like G in a gravitational field. So it shouldn't come as any surprise that the field line, since it's going vertically, it's not going to affect your horizontal velocity. It doesn't work like that way, but it's going to now introduce a vertical velocity, okay? In which case, then it becomes projectile motion. So that's pretty cool. Okay, but before we do that, we want to derive a few other little things so we can actually use them. So recall that we got F equals to charge Q times by E. Okay, that's one of the first thing we defined. All right, now we want to say or want to then recall Newton's second law, which is ma equals to Q times by E. Okay, so I can have acceleration equals to Q times E divided by m, and this is the fifth equation that we're going to use in this topic. Okay, so so this is saying that, well, since we have uniform E, since we have uniform electrical field strength, no matter whether you're here or you're here, okay, and your charge is constant because the charge doesn't, you don't get greater charge or less charge by moving through the electrical field. Let's assume that we're moving vertically at this stage. And the mass shouldn't change unless you're losing mass along the way, which means your acceleration should be constant no matter where you are in the field. And that's pretty cool. And since it's a uniform field, it's like it's kind of like the gravitational field is near constant when you're near the surface. Okay, so I think that's a pretty cool fact. Now, since we know that it's projectile motion, what does that mean if you say, if you start from one side here, and that's a positive charge? Sorry, I apologize. If that's a negative charge and you have an initial velocity, if you have initial velocity, what's going to happen is it's going to track along, track along, track along, and it's almost like throwing a ball um, in a projectile, but eventually it's going to be drawn back into the positive side because negative is positive. Okay? So you're going to have few scenarios. If you start from the middle, and you're going to gradually go to one side, okay, assuming this one here is a negative charge, okay, and this side here is positive, as negative, okay, you're going to be drawn, and this one, that motion is a projectile motion. What other form of motion can there be? So parallel lines. Now, if you start from here, you're gonna have this motion like what you had before. Okay, so that's fairly straightforward. So in this case over here, okay, you're no longer traveling in a straight line, and you're actually curving on one side. Okay, so we have a particular term to call this. Okay, we call this deflection. So when a question asks you to find the deflection of electron or alpha particle or whatnot, and you're basically looking at how much vertical displacement there's been. Okay? So you're looking at the change in vertical displacement. So in this case here, that will be my deflection. All right, so now we're gonna do a quick question because that's all there is. Okay, so recall that your A equals to charge Q times it by electrical field 3E divided by M. We're gonna use this to do a few calculations. Okay, so this is page was it 157 on your workbook, question 12. Now know that this one in your workbook solution has an error, so you need to follow the solution here carefully. Okay, so blow this one up a little bit. Okay, explain, hang on, read the question first. Okay, uh, consider parallel conducting plate shown below. The magnetic field, magnitude of electric field between plate is 3.6 times 10 power 3 volts per meter. An electron fly horizontally midway between the plates with a speed of 2 times 10 to the power 7 meters per second. Electron traces a parabolic path towards the upper plate. Now, one thing you should note is currently we don't have the distance between the two plates, and we probably don't need to know. We'll probably never know. Okay? Now, secondly, this value here is my electric field strength. Okay, so the magnetic electrical field between the plate is my E, which is my delta V potential difference, and divided by D, the distance. Okay, explain why the path is parabolic. I'm just going to explain it. It's parabolic because oh, there we are. It's parabolic because it's a parabola, of course, but more specifically, if we know that there is now a acceleration towards that plate there, then in the presence of and assuming the initial vertical velocity